Today you're going to be looking at rational functions. Just a reminder, rational function would be written as the quotient of two polynomial functions, and we'll define those as a of x and b of x, where b is non-zero. And remember, b just can't be zero because we're not allowed to divide by zero. And here at the bottom, you'll see some of those examples. As a reminder, the rational function looks like this. So we know that if I were to build the table, it would have two parts. There'd be one piece down here in the third quadrant, there'd be another piece up here in the first quadrant. And just as a reminder as well, it's defined based on its asymptotes. So as it goes through any transformations, shifting up, down, left, and right, we would adjust the horizontal asymptote, and then there's this vertical asymptote. So both of them are located at 0. Today's lesson is focused on those two features specifically. So we have horizontal asymptotes. We've seen them, but we've not had to find them algebraically. So here it says that it's just the horizontal line that the graph gets close and closer to on the ends, but will never touch. And that's your horizontal asymptote, and it's always going to be defined as y equals some number. Vertical asymptotes, we've already done a lot of work with these, so as a reminder, those are defined as x equals some number. When we go through and we try to find a horizontal asymptote, there's two different approaches. First would be that we're interested in what happens when the x values get really, really big or really, really small. So we're going to use a table to generate these possible values. And notice it does say here that you can use the table function of the calculator. The values that we pick are just sort of arbitrary. So just to illustrate the point, right here, these represent values that get huge to the right of 0. So these would be positive values. And so it'd be like 10 and then 100 and then 1,000. And again, I'm just randomly picking these, showing them getting significantly larger. Down here at this end, these would be our negative values that get significantly smaller. So similarly, we'll stick with -10, -100, -1,000. So we would let the calculator put these values into the function and generate the outputs. If you looked at the table or if you evaluated the function, you would see the following output values. So here you can see if I wanted to define the horizontal asymptote, I'm looking at what is the graph approaching but not touching. And it's pretty clear that it's getting closer and closer to +6. So we would have a horizontal asymptote at y equals 6. Now it's not always desirable to build a table each time. So here's an example of an alternative. So the shortcut is defined by comparing the degree of the polynomial in the numerator with the degree of the polynomial in the denominator. And so here for this first example, if both polynomials are the same degree, divide the coefficients of the highest degree term. So you are looking at just those first two. And so the idea here being that if I were to divide these, the x squareds cancel. 6 divided by 2 would just be 3, and so this would be y equals 3. And the reason this happens is if I were to build the table and the x's become really, really big or really, really small, it's those leading coefficients that will sort of stay. Then here for number 2, this is just talking about, well, what if those degrees don't match? So instead of memorizing what this says, so here it says if the polynomial in the numerator is a smaller degree than the denominator, the x-axis is the horizontal asymptote. So you could memorize that, but I like to carry forward the same sort of shortcut that was first talked about. If I were to look at the highest degree, I see that it's an x cubed in the denominator. The numerator doesn't have that, but I could put a placeholder in and say that there is a 0x cubed up there. And so then when I go through and divide, you'll see like the x cubes cancel. 0 divided by 2 is still 0. And so this would be located at y equals 0. The third example, again, I'll let you read that, but it's talking about what happens if the powers don't match. but you could always take the same approach, which is to say x squared is the highest degree, and then there's no x squared in the denominator, so this could be the same thing as x squared divided by 0x squared. The x squared cancel. We would have like 1 divided by 0, and that would be undefined, so there would be no horizontal asymptote in that case. Now, as a reminder for how to find the vertical asymptotes, you do focus on the denominator, but the part that's going to be slightly different is that we could have another algebraic expression in the numerator. So step number 1 is going to be to just factor the numerator and the denominator. Next thing you're going to do is check if any of the factors cancel. If they do, those are defined as the wholes. Once that's completed, you can set each factor equal to 0, and then that's where we will find the zeros. Then obviously write them all in the form of x equals some number. So here we have 4 examples that we'll go through, and we're going to work on finding the horizontal and vertical asymptotes for each of them. So for the first one, horizontal asymptote first. So I noticed that x is the highest degree, and it's in the bottom, so the top does not have an x, so it could be like 0x over 1x. X's cancel, 0 divided by 1 is 0. So your horizontal asymptote is located at y equals 0. Then for the vertical asymptotes, so remember we got to factor completely. In this case, everything is completely factored, so I focus on the denominator for when does x minus 3 equal 0, and that happens when x is equal to 3. So on to B, looking at the highest degrees. We got an x squared in each, and so we're just ready to go ahead and divide to determine the horizontal asymptote. The x squareds cancel, and we'd have 2 divided by 1 or just 2. So horizontal asymptote is at y equals 2. For the vertical asymptote, we would factor completely. To save us some time, the numerator here is not factorable, so it just stays as the trinomial, but the bottom does factor into x minus 1 times x minus 1. So you'll see nothing cancels, so the horizontal asymptotes, even though there's 2 factors, is only located at x equals 1. For C, so x squared is the highest degree, and I don't have that in the numerator, so it would be like 0x squared divided by 1x squared. 0 divided by 1 is 0, so horizontal asymptote at y equals 0. For the vertical asymptotes, I'm going to factor completely. So the numerator is factored, or in its simplest form. The denominator has a GCF of x, so we have x times x minus 2. And I do notice that the x minus 2's cancel. So reminder, that tells me that at x equals 2, we would have a whole. But then here at x equals 0, that's the vertical asymptote. And then for our last one here, the degrees match. So the x squared cancel, and we're just left with 3 over 2. So I'm going to leave that as a fraction with the horizontal asymptote at y equals 3 over 2. And then for the vertical asymptotes, we will factor completely. In this case, the numerator is factorable. And so to save us some time here, it factors into 3x plus 1 times x minus 1. You could use guess and check or the master product method to get that. And the denominator factors into 2x minus 1 and x plus 2. So I see here that nothing cancels. That means we don't have any wholes. And since there's 2 factors down here, we're going to have 2 vertical asymptotes. So one of them is located at x equals 1/2, and the other one is located at x equals -2. And that takes care of what you need to know to be able to get through the homework. Good luck.